Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Markov and Chebyshev's inequalities. Let's start with some motivation. In a previous video, we saw we established the law of large numbers, which tell us that if we have some independent random variables with a certain bounded mean and bounded variance, then if we look at the deviation between the sample mean when we average over n of these random variables and the true mean mu, the mean squared error goes to 0 as n increases, and in particular it goes to 0 as the variance divided by n. So that's great, the mean squared error goes to 0. However, you might be wondering, what does this mean in terms of the probability that there is a certain deviation between the sample mean and mu? Let's take a look at the picture. Here we see that in general, so what are we seeing here? This is some height data from the US Army, where this is the true population mean that we want to estimate. This is the standard deviation among all of the population, so it's bounded, and we have 4,000 people. And we're taking sample means over smaller subsets to try to estimate the population mean, which is here. And what we saw is that indeed, when we look at the variance of the population mean, as n increases, the variance becomes smaller. Now what we're asking is, sure, but what if we're interested in the probability that we have a certain deviation? So imagine that you have the probability that you deviate by 1 centimeter. Actually, I have the ability to draw straight lines, so I might as well. So we are interested in the probability of deviating by 1 centimeter, for example. What's the probability that we are out here? What's the probability that we are going to obtain points out there? It seems reasonable that that probability should also go to 0, right? Because otherwise, the standard deviation or the variance of the estimator around the true mean would not go to 0. But we need to establish it formally. From the picture, here this probability seems to be rather large, and it becomes smaller and smaller and smaller as we go on. There are less points that are outside. In this video, we're going to learn how to control probabilities or bound probabilities using the mean and variance, and this will enable us to establish that indeed the probability that there's a certain deviation from the true mean in the law of large numbers also tends to 0. It's not only the variance or the mean squared error. The prerequisites for this material are expectation and the law of large numbers. Okay, so we will start with the simplest inequality that allows us to bound probabilities using an expected value. This is Markovs inequality. It says that for non-negative random variables, if they have a small mean, then they cannot take large values with high probability, which is kind of common sense, because then they would have larger means if they could take large values with high probability. We're going to establish Markovs inequality first for discrete random variables, because I find the proof more intuitive than the general proof, although as you will see, the general proof is really simple and elegant. But I find that this proof really shows you why it holds. So imagine that you have a non-negative discrete random variable A with a certain range, and you fix a constant C. And now you want to bound the probability that A is greater than that constant, and you want to use the mean. In order to do that, we're going to write the mean by the definition as the sum of all the possible values of the random variable times their corresponding probabilities. And now we're going to separate these possible values into the ones that are greater than C, which are here, and smaller than C, here. For those that are greater than C, we realize that we can actually lower bound this value A by C, but just for those. Okay, if we do that, we obtain this inequality where the whole mean is lower bounded by the part of the sum that corresponds to values smaller than C, and the part of the sum that corresponds to values greater than C, where we have replaced A by that constant. Now, if we eliminate this, this is kind of nice because we get a lower bound on the mean in terms of the sum of the probabilities of all the values that are greater than c. That's just equal to the probability that the random variable is greater than c, and that's exactly what we want to bound. So now we have to flip things around a little bit. Okay, so this is non-negative, okay, because all the a values are non-negative. So we end up with this lower bound for the mean. This lower bound is exactly in terms of the probability that a is greater than c, which is equal to this sum here. Okay, that sum is going to be small or equal to the mean divided by c, because remember that c is non-negative, or is actually positive. So we have that indeed the probability that the random variable is greater than a certain constant is bounded by its mean. Okay, the smaller the mean, the smaller the bound on the probability. So this is the general result. This holds for all random variables, not only discrete random variables. If you have a non-negative random variable and you fix any positive constant, the probability that the random variable is greater than that constant is always bounded by the mean divided by c. Now we're going to do the more general proof, which is really simple and elegant, but I feel that it can be a little bit mysterious the first time you encounter it, which is why we did the proof for discrete random variables in detail. Okay, so we're going to establish the general result. We're going to define a random variable, which is Bernoulli, which is equal to 1 if the random variable is greater or equal to c, and 0 otherwise. Now we realize that we can build a random variable a minus cb, which is always non-negative. Why? Because when this happens, a is greater than c, and when this happens, b is 0. So this just means that a is non-negative. Okay, so in particular, this means that the expected value of this random variable that we have here is going to be greater or equal to 0. If we expand this using linearity of expectation, we get this inequality. And now the expected value of this is just a Bernoulli random variable with parameter equal to the probability that a is greater or equal to c. Okay, or I don't even need to get fancy and set this as a Bernoulli random variable. What's the mean value of this? It's just 1 times the probability that it equals 1, right? So that's the probability that a is greater or equal to c. And we get exactly the same inequality by dividing by c on both sides. Again, this is a super simple, elegant proof, and it illustrates the spirit of a lot of these concentration inequality proofs. But I think that the first time you see it, it might be a little bit mysterious. Essentially, it encodes what we did for the discrete random variables. Let's do an application of Markovs inequality. The mean age of NYU students is 20 years. Let's bound the fraction of students that are above 30. So we have this random variable a. I pick a student at random. What's the probability that they're older than 30? This is going to be bounded by the mean age divided by 30. The mean age is 20. The probability is at most 2/3. Okay. Usually, or well, often, we're interested in not bounding the probability that non-negative random variables are greater than a particular value, but rather that random variables deviate from their mean. And that's what we needed for the law of large numbers. This is what Chebyshev's inequality achieves. It's just essentially an application of Markov's inequality to that case. Chebyshev's inequality says a random variable with small variance cannot be far from its mean with high probability, because if it were, then it would have to have a larger variance. That's the intuition. More precisely, for any constant c and any random variable a with bounded variance, we're going to see the probability that a deviates from its mean in squared distance by more than c. Here we realize that we can just call this thing be another random variable that is a minus its mean, okay? And in particular, we square it, so now it becomes a non-negative random variable. So now this non-negative random variable, okay, this is just equal to the probability that this non-negative random variable is greater than c. We know how to bound this, right? Markov's inequality. This is just the expected value of b divided by c. That's what it is. Now, what is the expected value of b? According to the definition of b, which is down here, this is just the expected value of a minus its mean squared divided by c. Okay, so we get this inequality here. But now what is the expected value of a random variable minus its mean squared? That's just the variance by definition. So the probability that the squared deviation is above c is just is bounded by the variance of the random variable divided by c. Imagine that you wanted to bound the absolute value deviation, okay, by a certain amount d, then this would just be equal to the probability that the square deviates by d squared, right? Because we're going to often apply it like this. This is just bounded by the variance of a divided by d squared. Okay, so that's just so that if in some of the subsequent slides you see that there is a constant here and a constant squared here, that's just because we're considering the absolute value as opposed to the square. Okay, I hope I didn't make that more confusing than it needed to be, but just in case, just in case you're wondering in some of the subsequent slides. An important consequence of Chebyshev's inequality is that if you have a random variable with variance 0, what does that mean? What does that mean that a random variable has variance 0? We are going to see that it means something very concrete. Let's consider the probability that the random variable deviates from its mean by epsilon. Now we're going to bound this with Chebyshev's inequality because we don't have a square here. That's why we're going to have to put a square there, okay? Because this is the same as squaring on both sides. Maybe I should have just explained that here because it's just much cleaner. Anyways, we have this inequality for by Chebyshev's inequality, we have this bound for every possible value of epsilon. And now if this guy is 0, this is equal to 0 for every value of epsilon. So the probability that the random variable deviates from its mean by, even a minuscule amount is always 0. This establishes that when a random variable has variance 0, it's just equal to its mean. Okay, the probability that it deviates from its mean is 0. It's just there. It cannot move. It's a constant. Okay, equal to its mean. Which is not immediately obvious when you introduce variance, that it would constrain, setting the variance to 0 would constrain the random variable in this way. Chebyshev's inequality establishes that this is the case. Now let's apply Chebyshev's inequality to this problem of bounding the age of students. We're going to bound the fraction of students that are above 30. We're going to bound it by the probability that the age of the student deviates by 10 from its mean, right? Because the mean is 30. Notice that this also includes the probability that students are below 10. That's probably not an issue. There's not many geniuses that come to NYU when they're 9 years old, or I hope for their mental stability that's not the case. But anyways, let me not get carried away. That's the bound that we're establishing. So now we have a deviation from the mean. By Chebyshev's inequality, this is just bounded by the variance divided by the square of this guy, because again, we could square on both sides. And now the variance is equal to 9, so we get a bound of 9%. Compare this to the bound of 2/3 that we obtained with a Markovs inequality. This is much, much tighter, which makes sense because we're using additional information about the distribution, which tells us that it's kind of tightly concentrated around 20. Markovs inequality cannot use that information. Okay, it also has to hold for distributions that are not as tightly concentrated around the mean. This is why this bound is tighter, and whenever you can apply Chebyshev's inequality, it is going to be tighter than Markov's inequality. Okay, and it is indeed quite a bit tighter. Okay, so let's go back to our example where we're looking at the law of large numbers. Okay, so we had these independent random variables with mean mu and variance sigma squared. This is the sample mean. We want to control the probability that the sample mean deviates from the true mean. We have established in a previous video that the expected value of the sample mean is equal to the true mean, and also that the variance is sigma squared divided by n. So this puts us in a great position to control the deviation between the sample mean and its mean, and mu, which is the mean of the population. Mu happens to be the mean of the sample mean. So, so this is the probability that m minus its mean is greater than epsilon. We can bound that by the variance of m divided by epsilon squared. Okay, this is just Chebyshev's inequality. And now, if we plug in the value of the variance there, it's sigma squared over n and epsilon squared. So this, for any fixed epsilon, if I look at at any epsilon deviation, it's eventually the probability of having that epsilon variation is eventually going to 0 if I take n to infinity. So this establishes that the probability of deviating by epsilon eventually converges to 0 once we take a large enough number of, we use a large enough subset to perform averaging, to compute the sample mean. In statistics, this kind of convergence, where the estimator, the deviation between the probability that the estimator deviates by any fixed constant from the truth becomes 0 eventually. When that happens, we say that the estimator is consistent. The sample mean is a consistent estimator of the true mean if you have independent identically distributed measurements. So again, this is just saying that if we look at any epsilon here, at any deviation of epsilon from the true mean, no matter how small we make this epsilon, if we take a large enough n, eventually the probability that we are outside of here is going to be 0. Okay, that's known as the weak law of large numbers. Let's go through another example in order to show that Chebyshev's inequality can actually give you some quantitative estimate of the number of measurements that you need for the sample mean to converge to a certain extent. So let us imagine that we are estimating the amount of people that have COVID-19. We have a certain total population of 8 million, and we want to have a probability of a 1% error that is less than 0.01. Okay, we want a deviation between our estimate of the prevalence of COVID-19 and the true prevalence. We want to make sure that that's going to be less than 0.01 99% of the time. So as you remember, the sample mean is random, right? Like we take a subset of people, we could be very unlucky. Could get a subset with low probability. We can always take a subset of people such that no one has COVID-19. But the point is that if we pick uniformly from the whole population, that's going to have low probability, and now we're going to make that that precise. Okay, but I'll show you in a moment what this means in terms of an equation, which I think will make it more clear. The question here is, how large should the number of people that we select at random be to ensure that our error is 1% or less 99% of the time? And an important question is, does this depend on the total population? And I want you to think about it. Like, do you think, if we had a smaller population of a larger population, would this change our result, the little n that we need to select? Think about it on your own. We will see what is the case, or what is the solution. Okay, so we have already seen that the tests that we take are independent and identically distributed. They're essentially a Bernoulli random variable. We saw this in a previous video, where the probability of picking someone that has COVID-19 is just equal to the proportion of people with COVID-19 in the population. So each of these guys is a Bernoulli random variable that has a mean equal to the proportion of people with COVID-19 and variance equal to theta times 1 minus theta. I've reverted to say theta instead of theta. Sorry about that. Okay, so the mean of the sample mean is equal to this parameter theta. I'm going to try to stick with theta because my understanding that that's the right pronunciation. And the variance is equal to the variance of the population divided by n. Okay, again, we established this in a previous video. So now we are going to, in order to use Chebyshev's inequality, we need the variance. We're going to control the deviation of the sample mean from its true mean, which is what we want to estimate. We have to control the variance. The problem is that the variance has this prevalence parameter that we don't know. So in order to control it, what we're going to say is, well, this prevalence parameter is between 0 and 1. So why don't we just bound the variance by 1 over n in order to be able to apply Chebyshev's inequality? And that's what we're going to do. Okay, so we want, and this is what I meant by the precise formulation of what we want. The sample mean is a random value, okay, that approximates this deterministic value, which is the the prevalence of COVID-19 in New York City. We want the random value to deviate from the true value by 1%. We don't want this to happen very often, basically. So the probability of this event, that this happens, we want it to be smaller than 0.01. When we take this sample mean, most of the time, we want the error to be below 1%. Okay, this is what we're saying. Notice that, again, this is the mean of the sample mean. So what we're asking really is that the deviation between the sample mean and its mean and not be greater than a certain constant. This is exactly Chebyshev's inequality, right? Here, we can bound this by the variance divided by that constant square. Because again, we could just take a square on both sides. Now we have said that we can bound the variance by 1 over n, and that's exactly what we do. So we get this bound of 10 to the 4 over n. When is this smaller than 0.01? When n is, I should have just flipped the slide, when n is greater than 10 to the 6, which is 1 million. This sounds like a lot of people to test. If you've heard of random sampling, in fact, for example, to determine the prevalence of COVID-19, this sounds like a lot. This is because Chebyshev's inequality is very strict, as it always holds. In a future video, we're going to see that applying the central limit theorem allows you to reduce, shows that you can get away with many, many, many less tests. But this already shows something really important, which is that the underlying population doesn't matter. The underlying population can have like 200 billion people. It doesn't matter. If you're only interested in the prevalence, in what percentage of people have COVID-19, then the underlying population doesn't matter. We're just sampling from that underlying population, and we just want to know if 10% of them or 5% of them have COVID-19. For that, the underlying number of people has no influence. And if you think about this intuitively, it kind of makes sense, because this is saying that, okay, like if 5% of the people have COVID-19, if you pick 1,000 people, then and you look at how many of them have COVID-19, then around 5% are going to have COVID-19. That's going to give you a pretty good estimate of the whole population. It doesn't matter. The size of the population actually does not matter. Hopefully that was clear. So there's no dependence on big N. What have we learned? We have learned to control probabilities using Markov and Chebyshev's inequalities. And we have learned that the accuracy of estimates from random sampling does not depend on population size. We have also learned that the law of large numbers holds in probability. The deviation between the sample mean from the true mean when you have independent samples also goes to 0 in probability. Thank you very much.